This is a review of the various mechanical and chemical weathering processes that occur at the Earth's surface and begin the process of making sediment and sedimentary rock. Shown here is a weathered granitic outcrop along Interstate 8 in the Jacumba Mountain wilderness of Southern California. As we've talked about, the rock cycle is a descriptive concept map of the various processes that occur during a rock's lifetime. Once a rock is exposed at the Earth's surface, it is subject to weathering and erosion. Different kinds of weathering break rocks down or dissolve them, so the material can be transported away by different types of erosion. The two major types of weathering processes are mechanical weathering and chemical weathering. With mechanical weathering, rocks disintegrate and are broken down into progressively smaller pieces. This granitic outcrop displays the effects of mechanical weathering, common in arid desert regions. Chemical weathering involves the decomposition of rock. Limestone is a rock type that is susceptible to chemical weathering, especially in more humid tropical or subtropical regions. Both of these processes act on the rock in place. Erosion is the physical movement of material either by wind, water, or ice. Examples of erosion include sand and dust carried by the wind, sediment carried by streams or glacier flow, currents in the ocean, etc. Material can be both physically and chemically weathered as it is being moved. Mechanical weathering includes processes that break rock into smaller pieces of the same composition as the parent material. This has the progressive effect of increasing the surface area of the weathered material and can greatly increase the effectiveness of chemical weathering as well. Frost wedging is a mechanical weathering process where the daily temperature alternates above and below the freezing point of water. During the day, water can seep into bedrock if it is highly fractured or jointed. As the temperature drops below freezing, the water freezes and expands by about 9%, exerting pressure on the walls of the crack. The water melts as the temperature rises again the next day. This cycle repeats until the water drains away. Over time, this process acts like a hydraulic jackhammer, progressively widening and lengthening the fissures in the bedrock. The effects of frost wedging can be seen clearly in places like Arches National Park in Utah. This is the fiery furnace area of Arches National Park. It's a maze-like landscape of sandstone fins, created as weathering and erosion occurred along a prominent joint set. These near vertical joints are formed in the Middle Jurassic slick rock member of the Entrada sandstone. This area is also home to a number of arches, including Walk-Through Arch, Skull Arch, Kissing Turtles Arch, and Surprise Arch. Frost wedging that occurs along cliffs produces falling rock debris that accumulates at the base of the cliff. This rock debris pile is called talus, which typically forms a steep talus slope. If the debris is relatively fine-grained, it is referred to as scree. Exercise caution if you are hiking on a talus slope and you notice it is layered with relatively fresh debris. That may mean recent rockfall and rock avalanche activity. The mechanical weathering process of thermal expansion and contraction takes place in areas where there's a wide range in daily temperature. Rocks expand at higher temperatures during the day and shrink slightly with lower temperatures at night. Repetition of this process over time can effectively shatter rocks, especially when combined with frost wedging. This process is relatively common in arid regions where there can be wide swings in daily temperature. One of these areas is shown here, West Mitten Butte in Monument Valley. This is West Mitten Butte in Monument Valley. The valley floor and lower slopes of the buttes are formed in the relatively soft Organ Rock Shale, Permian in age. The slightly younger, massive Deshay sandstone forms the bold 400-foot-high cliffs of the buttes in this area, and the sequence is capped by the horizontally layered Middle Triassic Moenkopi Formation. As with Arches National Park, the Monument Valley area of northeastern Arizona can experience a wide range of daily temperatures, and this aids in the weathering along bedding plains in the mudstones and in the vertical fractures of the massive sandstone. Other mechanical wedging and expansion effects include the growth of salt crystals and plant roots. Each may widen fractures in the rock. Common in arid climates, salt wedging occurs as crystals precipitate and grow from saline water that has infiltrated cracks in the rock. Organic activity, such as the growth of plant roots, can also exert pressure to create and widen fractures, and is commonly seen in urban areas. Exfoliation, or pressure release, is another mechanical weathering process. This occurs when a large mass of rock with rather uniform composition, like a granitic pluton, is uplifted to the surface. The decreased confining pressure causes cracks, fractures, and sheet joints to form parallel to the unloading surface, or usually the ground surface. Frost wedging and thermal expansion and contraction subsequently add to the weathering effect. Areas of exposed granitic batholiths commonly show signs of exfoliation. Sheet joining is pervasive in rocks of Yosemite National Park, including at Half Dome. This is the view to the southeast of Half Dome in Yosemite National Park. With the formation and uplift of the Sierra Nevada mountains, the massive Jurassic granites here have been exposed and glaciated. This has caused pressure release to form extensive sheet joints in the granites, roughly parallel to the exposed surfaces. Chemical weathering involves the chemical alteration and decomposition of parent material in place. Chemical weathering processes are accelerated in areas of higher temperature and humidity, like tropical and subtropical regions. This is an issue for limestone or marble-based features from gravestones to monuments to ancient buildings. Located in the sprawling metropolis of Athens, Greece, the Parthenon, or former temple to Athena, is one of the most important surviving structures of classical Greek civilization. Construction started in 447 BC and was completed about 8 years later. At least 20,000 tons of Pentelian marble were used in the construction of the Parthenon, and as with any carbonate rock or marble, chemical weathering will occur when exposed to a more humid climate. This is an issue for limestone or marble-based ancient buildings like this one. Some minerals are more resistant to chemical weathering, and some are more susceptible. This shows a list of various minerals and their stability under weathering. Calcite and halite are relatively soluble, and so they're not very stable. The same can be said for the silicate minerals olivine and the feldspars. Those are the minerals that typically weather the fastest. Conversely, the clay minerals and quartz, aluminum hydroxides, and iron oxides are fairly stable and weather the slowest. So these types of minerals are typically left over after weathering and are present in significant abundances in resulting sediment. Important types of chemical weathering are hydrolysis and dissolution, where some minerals, and thus rocks, dissolve in water and weak acidic solutions. In short, hydrolysis is where only part of a mineral is dissolved, and the rest is transformed into a new solid material, like a clay mineral. Dissolution is where the mineral dissolves completely. A common example of this process involves weak carbonic acid. Natural rainwater is slightly acidic, as falling rain absorbs carbon dioxide in the atmosphere, making a weak carbonic acid. This very weak acid interacts with surface rocks, where certain minerals like feldspar are susceptible to hydrolysis and dissolution. Ions like potassium, silica, and bicarbonate are liberated from the feldspar and taken away in solution, whereas the remaining feldspar is transformed into clay minerals. The mineral calcite, and thus a rock containing calcite, is also susceptible to this process, as well as dissolution involving dilute hydrochloric acid. In fact, the effervescence of calcite, and thus limestone, with dilute hydrochloric acid, is a diagnostic physical property that we use to test for composition. Silicate and carbonate minerals are susceptible to dissolution and hydrolysis, where some of the original minerals are converted to secondary clay minerals. Ions like silicon, sodium, calcium, and potassium are carried away in aqueous solution, meaning water, leaving a clay mineral residue enriched in aluminum and silica. Making coffee is a great analogy for mechanical and chemical weathering. First, you have to grind the coffee beans. Why do we do this? This mechanical weathering creates more surface area for the hot water to leach the goodies out of the beans. Have you ever made coffee without grinding the beans first? That would be pretty weak coffee. Then, hot water, or hydrothermal fluid, passes over the coffee, extracting soluble material and carrying it away into the coffee pot or the mug. This is similar to how chemical weathering extracts elements like sodium, calcium, potassium, silicon from the rock and carries it away in streams and groundwater. The remaining solid coffee residue, now depleted in its soluble elements, represents the clay minerals and other insoluble material left behind. Through the process of oxidation, many minerals react with oxygen to form oxides. Dissolution of iron-rich minerals produces iron that can combine with oxygen from the air or water to form iron oxides, like the mineral hematite. This is essentially the process of rusting. These iron oxide-rich sands are located in Monument Valley. And we're looking towards the Totem Pole and Yebiche, located just to the southeast of the Mitten Buttes in Monument Valley. And the weathering and erosion of these rocks produces orange to tan colored sand, which forms superficial deposits that cover the bedrock and collect in dunes. Notice how the wind has pushed the sand up against the sandstone cliffs. Spheroidal weathering occurs in jointed, compositionally uniform bedrock. Surface water acts to round the edges of fracture surfaces, with weathering progressing inward via groundwater processes. Large granitic exposures typically weather to rounded boulder fields due to this type of weathering, like here along I-8 in Southern California. Organic activity can also yield chemical weathering effects. Biological organisms like moss, lichen, etc. can produce organic compounds that can form acidic solutions that chemically weather rock surfaces. The Jacumba Mountains wilderness east of San Diego is underlain by an expanse of Mesozoic granitic rocks. This terrain locally displays well-developed spheroidal weathering in the fractured granitic rocks. Here, Interstate 8 follows Myers Creek, which has helped to form the Inkapa Gorge in this area. Alcoves are recessed areas of cliffs that can form in arid regions by the process of spring sapping. This is where groundwater that flows down through the rock encounters an impermeable unit and is forced to move horizontally. A spring is formed where the groundwater exits the cliff, usually near the boundary between rock units. Further groundwater flow is then concentrated into this area. The spring water acts to dissolve the rock or the cement binding the grains in the rock, thus eroding into the cliff. Over time, the cliff face becomes curved and an overhang may develop, forming an alcove, much like this one in Marble Canyon of Grand Canyon National Park. Interestingly, this is one of a set of alcoves named Royal Arches, when they are actually alcoves and not arches at all. And given the nature of groundwater flow, spring sapping leaves a distinctive mark on the landscape, as can be seen in the Grand Canyon, with its innumerable amphitheater-like stream drainages walled by scalped cliffs. Here's the eastern portion of Grand Canyon National Park. Even from high altitude, the distinctive amphitheater-like drainages are readily apparent. Every major tributary canyon possesses the same characteristic morphology, with steep, scalloped walls and a rounded upper end. Here's the Pipe Creek drainage between Mather Point and Yaqui Point. Arches are formed in different ways in several different types of environments, from wave erosion along active rocky shorelines to weathering and erosion of jointed bedrock in arid regions. In the cold semi-arid desert, where Arches National Park is located, the geology is well suited for arch formation. Long ago, the sedimentary units in the area were bowed upwards, forming distinctive joint sets in the relatively brittle units, like the slick rock member of the Entrada sandstone. The slick rock is a quartz-arenite unit, mostly composed of quartz grains, cemented together by calcium carbonate. Progressive weathering and erosion along the parallel joints in the sandstone form vertical fins. Water percolating down through the permeable sandstone fins eventually encounters the relatively impermeable Dewey Bridge member of the Carmel Formation, forcing the groundwater to move horizontally and ultimately out of the rock. Dissolution of the calcium carbonate cement in the sandstone causes erosion of the cliff face, eventually forming alcoves on either side of the fin, which eventually connect to form an arch. Here is Delicate Arch, one of the most famous arches in Arches National Park. It's 52 feet in height, with the slick rock member of the Entrada sandstone forming the lower half of the arch, while the Moab member of the Curtis Formation composes the upper half. The arch got its current name in the 1930s, but was originally known to local cowboys as the Chaps and the Schoolmarm's Bloomers, among other names. Middle Jurassic sedimentary rocks form the landscape in the area around Delicate Arch. The area immediately around the arch and the lower half of the arch are in the slick rock member of the Entrada sandstone. The upper part of the arch is in the Moab member of the Curtis Formation. Both units are aeolian sandstones, or wind-deposited sandstones. The small basin adjacent to Delicate Arch is called a panhole, a weathering feature that most commonly forms in sandstones and granitic rocks. The Colorado Plateau's geology and semi-arid climate provide perfect conditions to form mesas, buttes, and pinnacles. These features all form by cliff retreat, otherwise known as scarp retreat, which starts with the mechanical weathering of a resistant, jointed cliff-forming unit, like a massive sandstone. Weathering and erosion of a weaker underlying layer, like a mudstone, then undermines the cliff former and causes its failure. Stream and wind erosion may further undermine the cliff. With time, cliff retreat forms progressively smaller features, from large plateaus down to smaller mesas, to even smaller buttes, to pinnacles and spires, the last vestiges of a once much larger landform. Of course, Monument Valley provides numerous magnificently exposed examples of all of these landforms. Near its almost identical twin, East Minton Butte is located in Monument Valley, less than a mile from the Arizona-Utah border. Here are the Mittens and Merrick Butte in Monument Valley. East Minton Butte's geology includes the Organ Rock Shale forming its sloping base, the massive cliff-forming Deshay sandstone, thin horizontally bedded Moenkopi Formation mudstones, and the Shinnerup conglomerate of the Chinle Formation, capping the very top. During the Laramide orogeny, which began about 70 million years ago, these sedimentary layers were tectonically arched upward, forming what's called the monument upwarp. Stresses related to this folding created the joint fractures in the more brittle units, like the Deshay sandstone. It's amazing to think that the rock layers in the now isolated buttes and mesas were once connected. Karst topography, or karst for short, is a landscape dominated by dissolution processes and their resulting features. Naturally acidic rainwater, stream water, and/or groundwater dissolve soluble rocks like carbonate rock and evaporites. This typically occurs in regions with humid climate. Different stages of landscape development can be recognized, commonly including sinkholes and solution valleys, and of course, caves and caverns beneath the surface. Many parts of the Appalachian Mountains region display this karst topography, as do large parts of Tennessee, Kentucky, Indiana, Texas, and most of Florida. Several areas in Southeast Asia display advanced karst terrains that include tower karst in some places. This area of Southeast China displays a karst landscape. In some areas, the dissolution of jointed carbonate rock has formed a jagged array of conical peaks and narrow valleys. In other places, the erosion has reached its minimum base level and formed isolated near vertical towers, what is known as tower karst, most common in tropical regions like Southeast Asia. Well, that's all for now. Till next time.